right, I have some exciting news for you. This is the last analysis we will talk about in 8307. Yay, last new thing to learn. All right, and the good news is, like I've said probably way too many times before, all these analyses follow the basic same process. They're just a little different depending on your research scenario. So let me go to our chart and put this last one. You have to excuse my writing from before. I'm just gonna open this real quick. Thank you. All right, in our chart, I'm going to here put ANOVA. So that stands for Analysis of Variance. So we will be analyzing the variance between and among some samples. So this test is used when we want to compare more than two groups, or I should say two or more groups on one outcome. So Anova and independent samples t-test function just the same. They are identical when you only have two groups. Anova, however, can handle more than two groups. So I'm just going to say this test is used when we want to compare two or more groups on one outcome. So we are still limited to one outcome, but now we can compare more than two groups. So if we have grade levels in a school, or if we have a couple of different treatment groups and a comparison group, whatever the situation is where we have two or more groups, we can compare them on an outcome. So let's talk for just a second about ANOVA, and then we'll get right into an SPSS example. So there are many research examples where ANOVA is appropriate, and I've just listed a few here, such as does reading comprehension differ according to how a passage is organized? So reading comprehension would be your outcome, and then organization would be your grouping type. So maybe you have it organized in 3 or 4 different ways, and you want to compare, does comprehension differ based on how it's organized? Do educational aspirations differ by student ethnicity or student SES level? Does the decision-making style of school principals make a difference in teacher morale? So you have an outcome of teacher morale, some sort of morale measurement, and then you're comparing different leadership styles. Do SAT scores differ by college major? And again, in an independent samples t-test, we did these same types of things, except we were limited to two groups. And ANOVA kind of opens the door for us where we can look at more than two groups. All right, so the question is sometimes, why not just run several t-tests, right? So if you have 5 groups, you could just do all the possible pairwise comparisons, 2x2 comparisons, and run several t-tests, okay? So if you look at the next bullet, I have the number of comparisons is k times k minus 1 divided by 2, or k is the number of groups. So 5 times 4 divided by 2 is 10. So you would need to run 10 t-tests to make all those 2x2 group comparisons rather than one ANOVA. So this presents several problems, but I think the most important one to think about is we've been talking about the 0.05 level, or that alpha level, or that P critical level. Well, that is also our type 1 error rate. So we're essentially saying, when we run a test and we evaluate significance at the 0.05 level, we're saying, okay, well, I'm willing to be wrong 5% of the time. I'm going to set that. My probability doesn't have to be 0.000. It can be a little bigger than that, and I'm willing to take that risk. Okay, so in ANOVA, you have that risk one time, right? So you run an ANOVA comparing your 5 groups one time. So for your experiment or your experiment-wise error, it stays at 0.05 because you're only running one analysis. But imagine if you were running 10 analyses, every time you run an analysis, you're willing to be wrong that 5% of the time, or that type 1 error rate is set at 5% each and every time. So over your entire experiment, you're much more likely to come to a wrong conclusion, or your error rate is much higher than with just running one ANOVA. Okay, so you can kind of see the benefit there where our error rate is better controlled. Okay, there are several types of ANOVA, and we are going to talk about several of them in 8304. But for this course and this first look at ANOVA, we're going to stick to a one-way ANOVA. And in a one-way ANOVA, you have one independent variable or one grouping variable, and then you have one dependent variable. All right. What's happening in an ANOVA is kind of illustrated here. So in this case, we have 3 groups, and the means of your 3 groups are being compared on whatever outcome you're selecting. Maybe it's GPA, maybe it's a depression inventory, maybe it's a self-efficacy measure, and you want to compare 3 groups on whatever that outcome is. So when you calculate the means of your 3 groups, SPSS is going to compare those means, and you can kind of visually see, if I'm looking at these means, how different are those distributions of scores, right? They may not be different enough for you to find statistical significance, as compared to this situation where when SPSS compares the distributions, compares the means, you may pick up a difference here, and it might be a statistically significant difference. Now, I'm just totally eyeballing these and making a judgment just based on experience. Means that are close together probably and have similar variances probably are not going to be statistically significantly different. And then vice versa over here. Means that are further spread apart but still have similar variances. They this type of result would be more likely to be statistically significant, let's say. All right. In ANOVA, what we're doing is comparing a couple of different types of variation or variance. And those types are within group and between group. So let's talk about within group first. Imagine if you are comparing 3 groups. Maybe you have a treatment group and a second treatment group and a comparison group. Well, within your treatment groups, treatment 1 and treatment 2, and your comparison, individuals are going to vary on whatever that characteristic is that you're talking about. So what if we're looking at self-efficacy? Maybe self-efficacy of teachers. And in treatment group 1, they've had a certain type of mentoring. Treatment group 2, they've had a different type of mentoring. And then you have a comparison group that's had no mentoring. Okay. Well, within each treatment group and the control group or comparison group, people, even within the same group, are going to have different levels of self-efficacy, right? So that is just a reflection of inherent variation among individuals, even within the same group or given the same treatment, right? Even if we give 2 people the exact same treatment, they're not going to respond identically to it, right? So within group variation is the amount of variability or variation each individual group has within itself. So within the group variation is where this kind of comes from. And that, to me, that helps me remember it better. If I think, okay, within group variation is within each group, how much are people differing? Okay. The other type of variation is this between group variation, right? So now it's comparing the variability between the groups. So treatment group 1's variability compared to treatment group 2's variability compared to treatment group 3's variability. All right. And it's going to be simplified by sum of squares between. When the null is true, the amount of variance within and the amount of variance between will be the same. All right, so if you think about the null says there are no differences between or among my groups, right? Whatever the situation, the null is always the same. The null always says there are no differences. And in this case, in an Anova, it's saying there are no differences between my groups, right? So when the null is true, that variability within, so looking at each group independently and how variable people are on, say, self-efficacy, comparing that amount of variability with the amount of variability we have between our three groups, when the null is true, there will be no comparison. There'll be no differences. They'll be the same. Okay? Now, let me back up and say, when the null is not true, when we reject the null, that is saying that when I'm looking at each group within itself and I'm comparing between groups, there are differences in that amount of variability. So when I'm going to reject the null, I'm going to have the opposite of what's happening here in this last bullet. And remember, variability is how people are scoring on that characteristic of interest. Okay, so if the variability between the groups is different, then that means they're scoring differently on whatever that characteristic is. All right. Now, the test statistic this time, and rather than Z or T, is going to be called F. That F statistic is actually calculated by dividing how much variability there is between groups by how much variability there is within the groups. And when F equals 1, then that means there are no differences. So how further away F is from 1, the more likely we are to reject the null. So when we look on our SPSS output and we see an F of 10, then we're going to know, well, that might be statistically significant because it's pretty far from 1. And the more ANOVAs you run, you'll become more and more accurate with your kind of eyeball estimations. You know, when you start seeing large F values, you're going to get an idea of, okay, that's probably just statistically significant. Kind of like you were doing with the Z tests and the T tests. All right, so to assess statistical significance, we're going to do the same thing that we've been doing. Now, I have a note here about a table in your book. So just like the Z and just like the different forms of the T tests we were using, there is a table or tables that have been developed that a researcher can examine and figure out that F critical value, just like we did Z critical and T critical. We can follow that same process. Now for us, we're going to be doing more of the SPSS application, so we won't actually turn to the table in the book, but you can for sure, and it's not a terrible idea to practice doing that and kind of maybe wrap your head around what's happening behind the scenes in SPSS. But when we run an ANOVA, we're going to have this ANOVA summary table, right? So the source between groups, the sum of squares, that's that variability between your groups compared to the variability within your groups, okay? So this measurement, this sum of squares between the groups is what we talked about before. It's if we compare the variability between the groups, how much is there? And then how much variability is there within the groups, looking at sum of squares. Now, if you were an ed research major, we go through and learn how to calculate all this between the groups and within the groups. And so you see the math behind the table. And it's pretty interesting how it's done. But for a person who's not majoring in ed research or research design or something along those lines, ed psych, you really don't have to understand all the math that's going on behind it in order to apply it appropriately and know how it suits your research or not, or someone else's research or not. So we're just going to talk very generally about it being the variability between groups, the variability within groups, and then of course the variability total. The degrees of freedom is calculated by looking at the number of groups you have minus 1. And then the within groups is looking at your sample size minus the number of groups. And then you have your total. You have your mean square, and then your F value is calculated by dividing, if we did 14 into 111, we'd get this 7.75. And then we have our significance, or our p-value. Okay, so just a little idea of how the different parts of the Anova summary table work. So what does it mean to find statistical significance in Anova? Same thing as it's meant before for the other test. The result would signify that it's unlikely you would have obtained the sample means you did if the null was true. In other words, the means of your groups are differing. But just like before with the independent samples t-test, Anova does not tell us which groups are doing what, right? So when I look at this result here in this table, it's telling me, oh yeah, I found statistical significance, but it's not saying, well, it's between group 1 and group 2, or group 1 and group 3, or 2 and 3. It's not giving me that detail. It's just saying, yep, your groups are behaving differently. So in order to find out kind of who's doing what, we have the opportunity to run what's called a post-hoc test. So this after the fact test, we can run a post-hoc test to make all those pairwise comparisons. So we can see exactly which groups are behaving differently from which other groups, or where our biggest differences are among our groups. We'll click on it in a minute. You can see the very big list of post hoc tests that are available. A really common one is Tukey. There are a couple of other common ones. And which post hoc test to use is not something that you would need to keep, available in your brain for retrieval. What you would want to do is just have a great resource to go to that would describe each of the tests and what type of data situation it's appropriate for, and that way you could pick the one that was best for you. So in the absence of all that, picking a common post hoc test is perfectly fine. You can pick Tukey and you'll be good to go. The other part before we run one I want to touch on is effect size. So we know that statistical significance testing is impacted by sample size. And so I've kind of hinted at this idea of practical significance. And in Anova, it is eta squared or omega squared, but we're going to calculate eta squared, and I'll show you how to do that shortly. It's just a real quick little calculation. In other Anova analyses we do, eta squared is going to be calculated for you. Okay, so you don't have to do it by hand. But in a one-way Anova, we are going to do it by hand. It just takes 2 seconds. All right, so that is a quick run-through of Anova, the one-way Anova. And the next thing I want to do is take you through an example of Anova using SPSS. So that's where we'll pick up next time.